Oh, okay, logic gates, diode logic or diode and transistor logic. There's been some recent threads on one of the electronics forums I take part in about logic gates, and there's people having difficulty understanding some of the online or YouTube examples. And having looked at them, the reason they are hard to understand or don't work when people try them is a lot of them are either very, very poorly explained or fundamentally wrong. I mean, these are two common examples, which, as a purely hypothetical concept, are not too bad. But real-world applications, they are not much good, or plain do not work, in fact. So, the schematics, as a couple of the schematics, and this, if I zoom in a bit, is the physical representation of the thing's real components. So the first section is the AND gate. I suppose it's AND gate. Two diodes, cathodes to the inputs, anodes to a resistor to positive power, which is exactly what we've got here. Two diodes, cathodes to two separate tracks, or two separate strips, a resistor to power, and then that's connected to an LED, a resistor and LED to ground to show the status. And if I ground either of the inputs so they're not both at one level, there, I'll look at the camera to make sure I'm doing it right and look at the strip board at the same time, which is difficult. Grounding either of the inputs turns the diode off. So in a truth table sense, that is an AND gate. And to a limited extent, that will work as a real-world circuit. But the problem is, you can't cascade it. You can't just keep linking these together as you can a true logic building block type gate. As the diodes drop 0.6 to 0.7 volt typically. So as you try and cascade the thing, the output voltage will change. And if you're only cascading AND gates or diodes in the same direction, the output will be 0.6 higher than the input at each stage. So you go through 5 gates and you've got about 3 volts difference in levels. So you get to a very, very fuzzy and confusing state as to what level it's at. Because you could have 0 volt at the input of the first gate, and after a few gates you've got quite a significant voltage even when it's supposed to be showing a 0 out. The other thing is, you can't mix gate types using this type of construction. The next stage I've got here is an OR gate, which is basically the reverse of this. The diodes are the opposite way around, the resistor is to ground. You can see here, there's 2 diodes, cathodes connected together to the resistor to ground, and again a resistor and LED as a status indicator. So that will function in itself as an OR gate. If I connect power to either input, the output goes high, the LED switch is on. You see again the inputs are 2 separate tracks, and you can have multiple inputs as long any number of diodes you like, all connect to that common point as the output, and it will work. Now the problem is with that, as it is, it will switch fairly cleanly because it's not doing anything. Connect it to something else and you get problems. As they are standalone like that, they're okay to demonstrate the logic functions. However, you cannot cascade them because, or mixed types should I say, because the output level of one is only held by a resistor, and the next one is also a resistor, and if the resistors are to opposite power levels, voltages, they fight each other and you don't get a sensible level. So that AND gate is in a one state. Both inputs are floating high. The resistor is pulling it high. So on its own, you'd get the 9 volts, or as that's something you supply. But if I cross-connect that to the input of the next gate, that OR gate, because that works the other way around and the resistor's to the opposite side, I'll just demonstrate that first. The output of that is, okay, it's about 8 volts. Power supply is not exact. But you can see the voltage on that. If we connect that output to the input of the next gate, things will go pear-shaped. That level, rather than being a nice clean switch between high voltage and low voltage, is now half supply, because that resistor connects in series through a diode to that resistor that goes to the opposite supply. So no longer got a high or a low level, it's just halfway. So they are not cascadable gates. They're not practical for real-world applications a lot of the time. Sometimes diode logic can be used for some things. It can be used as a single stage, at least, for combining different IC outputs, inputs, and when you're playing with logic circuits. And it can occasionally be useful. Or converting a switching output that actively pulls high and low to an open collector output equivalent by using a diode so it can only pull low, or vice versa, so it can only pull high. So there are applications, but only in isolated cases. To get nearer to real-world practical circuits, you need to add transistors to boost up the levels again and give current gain. So each gate can drive other gates. Now, that's where you come to this one. This is a Nand gate, as typically shown in the internet. And again, as a hypothetical circuit, that's approximately right. But it will only work with perfect diodes, not real-world diodes, because the transistor conducts when it gets more than about 0.6 volts on the base, and the diodes drop about 0.6 of a volt. So even if you connect the diode to ground, you're not guaranteed to turn the transistor off, which is a bit of a problem, because that means it just doesn't do anything practical at all. I can demonstrate that here. That's what this stage is here. Now, I've added a resistor to ground from the base as well to help turn it off, that one there. So I'll go back to the circuit just to confirm, so you can see 2 diodes, the cathodes to the inputs, anode to a pull-up resistor connected to the base, then a resistor from collector to power, which is what I've got here. 2 diodes, cathodes to the inputs, anodes connected together and to a resistor to power, and then that white wire links that directly to the base of the transistor. The emitter of the transistor is grounded through the green wire, and that resistor there is on the collector to power as the output pull-up. Now then I've got 2 LEDs on it with higher value resistors, both connected to the collector, and then one to power and one to ground. So one's on for a high level output, one's on for a low level output, if it works. Now the problem is this circuit will not work. If I ground directly one of those LEDs, one of the input diodes, nothing happens. Just to prove the transistor works, if I ground the other side of the diodes, so that's directly the base, it switches. But grounding the diode does nothing. And that's not even allowing for the fact that in a real-world circuit, the previous stage that connects to that probably wouldn't give exactly 0 volts output. There'd be some slight voltage drop across the transistor or whatever was controlling it or switching the output. So it doesn't work. And then people see these circuits on the internet and wonder what they're doing wrong. they're not doing anything wrong if they try to copy it, because the fundamental flaws in the circuits. To make it actually work, let me just show the voltages first, so you can see why it's doing what it's doing. Actual voltages, just to demonstrate this. Try not to push things out of view again. So, with the inputs disconnected, that resistor is pulling the base up quite high. It's actually it keeps going up every time I look at this. I put a bit too much power through that transistor, really. It's a 1K resistor, so it's got about 8 MA through it. I'm approaching that, which isn't that high. It's not even doing enough to do any harm, really. But the voltage on the base is quite high, and the voltage on the collector is very low. If I short the input of one of those diodes, the cathode of one of the diodes to ground, so that's shorting one of these to ground here, doesn't matter which one. So it's attempting to pull the base to 0 volts, but with the voltage drop of the diode, which is 0.6 volt at least before it turns on. And the voltage on the base itself is still almost 0.8 of a volt, because the diode voltage drop is similar to the base drop, so it doesn't actually short the base out. And the collector voltage is still very low. So it just doesn't work. As a practical circuit, it's a joke, unfortunately. But that, again, very unfortunately, is typical of stuff on the internet and on YouTube. A lot of people just don't realise that their educational stuff, and these drawings are actually off a supposedly educational side, don't work, and they just confuse people. To make this work in a practical sense, it needs an extra diode or two adding. Rather than that link wire there, let's put a diode. There. You can see that's turned back on again. What I've done at that point there, I have added another diode. Yeah. So now, when the input is pulled to ground, let's start again. I have also got a resistor there. I've got a resistor from the base to 0 volts to ensure that when there's no connection to the base, it does properly turn off. That's again something that's missing for a lot of hypothetical circuits or a lot of internet circuits generally. If a transistor's effectively open circuited on the base, any trace of leakage can put some voltage on the base and cause it to slightly conduct. So unless the input is being actively driven low or to 0 volts, you should always have a resistor. It can be quite a high value, but it should always have a resistor to bypass any leakage from the base or leakage from the circuit to drive it even. Anyway, in this case, that other diode will drop 0.6 of a volt or so as well, the same as these. So if one of the inputs is pulled low, that point will still have about 0.6 to 0.8 of a volt on it. But that point there will be 0.6 volt less, so only, say, something like somewhere between 0 and 0.2 of a volt probably. So there's not enough to reach the 0.6 volt threshold to turn the transistor on. So if I try that now as a practical working circuit, if I ground one of those inputs, it should switch. There we go. So that's the first point. You have to allow for the real world voltages on circuits and how real world components work. And the next point is which I've never seen it. Well, sorry, there's one more thing. Whilst I'm looking at this, this is a Nand Gate. That indicates low. Both inputs are high, that indicates low. And that indicates high. When either input goes low, the output goes high, because it's not AND, it's an AND with an inverted output, or a diode AND with a transistor inverter, literally. Some of the people doing stuff on YouTube are, again, giving very, very bad explanations and just confusing people. So, NAND, the output is low when the inputs are high, and high when the inputs are low. So, in the logic or truth table sense for a NAND gate, that is the true output. That is on when it's high. That light is on when the output is high. So that's indicating a logic 1 state. Then the problem is then the person doing the demonstration will simply reconnect the LED, or have another circuit with the LED connected between the output and power, and then claim that's changed to an AND gate, which it hasn't. There's nothing different except how they're indicating the levels. That now does the same as the diode AND gate in a truth table sense, or ignoring the circuitry and looking at the indications. So either input being switched to low, the output goes low, apparently, but it's not. They're just reconnecting the LED. That's the center, the proper output, if you like, indication, if you like, that's on when the output's high. And just to verify, so if I take that LED out, it doesn't magically change the circuit operating mode. Change the indication, and that's all. So it is very, very important when you're looking at any kind of demonstrations that both the presenter and you understand if the logic levels are high for logic 1 or true, or low for logic 1 or true. And you can use either, as long as you make it very clear which you're doing, because it's quite common to mix logic when it's convenient, when you're building things with gates like 74 series or CMOS ICs. You can swap between the two as long as you know what you're doing and you make it very clear if you're explaining anything to anybody. But simply saying that because the LED's connected opposite, the gate works differently is complete rhubarb, nonsense. And it just confuses people, and I don't know why people do it. The only thing I can guess is they don't understand themselves what they're really doing. Anyway, it's a minor rant. But to get back to real-world applications, this functions as a static gate, if you like. Just using switches and LEDs, it works. However, you try and run this at any serious frequency to put it to practical use, even what by nowadays are very low frequencies, like 1 megahertz or so, which is what computers were running at back in the 60s and 70s even, when they switched to solid-state components rather than relays or valves, vacuum tubes if you want. This circuit will not work at anything other than very, very low frequencies, because, as I pointed out earlier, that transistor is saturating. It's turned on very hard, and the collector is being pulled down to millivolts. Now, I'm going to use an oscilloscope to demonstrate the frequency. And I'm going to screen record the oscilloscope so I can mix that in. So that's what this little circuit on the end I've kept out of view so far. That's a little oscillator. It's a 5-volt regulator, 7805 regulator to power it, and a little programmable crystal oscillator. And power leads are pushing things around. It's a 12 megs oscillator. It's got a built-in binary divider, and you can select which frequency you want from that divider by connecting the pins differently. I mean, these things, I think you can still get them, but this one's a leftover from stuff I was doing in the 80s, so it's not something I'm saying to use for a project. It's just something I have in the parts box that's convenient as a nice frequency source that I can select what I want to do with it. So I'm going to connect that to the input of that gate. That'll do. No, that's not one. I'm going to connect the output of that. Oh, that's what that grey wire there is. Let's float him out. I'm going to connect that to one of the inputs of this gate. I won't leave this in view. You don't need to see that. It's just that's producing about 1.5 megahertz wave from that signal, which I'll show on the scope. I just want to show what it was doing. So if I connect the oscilloscope probe here to ground and that input at the diode, and squeeze it through without pulling anything out too much. Right, so that's now showing a nice, well, not nice, it's fairly noisy because, again, a combination of the very long wire setup and loop using the breadboard and general things. It's got a bit of noise on it, but having some noise is not at all unusual in practical logic circuits, as long as the noise levels are well clear of the thresholds of the gates. And TTL thresholds are normally about 0.6 volts or less for a low level and 2 volts or higher for a high level, though they'll in reality it'll be about 0.2 volts and probably 3 volts or more on the output of the preceding IC. So there's a reasonable difference for noise to allow it to work reasonably reliably, as long as the designer takes proper care with decoupling and layout and things. Anyway, I'm getting sidetracked again. So that's the input, that waveform. For now, grab another probe. These are connected to a little Handtech USB scope box, by the way. Connect that probe to ground and look at the various signals. That's the resistor, which does next to nothing because it's only switching between ground and a fraction of a volt. Because the base stops it going above 1.2 volts because the series diode in the base. So that's still, again, very little on that. There's not enough to get a sensible signal out of that. Go to the collector and it's grounded. It's still, that transistor is saturated all the time because it's being driven hard enough that it never has time to unsaturate. The charge carriers in the silicon never have a chance to dissipate when the base voltage reduces slightly, and it doesn't turn off. So as a practical gate, it doesn't work at anything but very low frequencies. Now, the first thing to do to cure that or reduce the effect, and this is one of the early innovations in this back in the mid-60s, I think, is to use a diode clamp on it. Now, this is a Schottky diode. Schottky diodes conduct at about 0.4 volt or less rather than 0.6 volt as a conventional silicon diode. And notice that the base voltage needs to be above 0.6. The collector voltage was like 80 millivolts. So there's more than 0.4 volt difference between the two. So if I put that between base and collector, that will prevent the transistor turning on so hard. Now the problem is now that also that 0.6 volt, 0.6 volt, plus the logic levels, which you can see from the scope, the output of the oscillator doesn't go to completely zero, which is, as I said, it's normal. Things don't necessarily switch to theoretical levels, in real world, a lower level might not be quite zero. So the other fix to do that then is put 2 diodes in series from the pull-up resistor to the base. Which gives it an extra working margin, if you like. And now, guess what? Let me put a probe on that, a clip on that, so I'm not holding it. Go back to the collector. Is it one of the points on the collector there? Yeah, I can do it without pulling the resistors out. Let's try and twist that probe around a bit. There. Right. I mean, it's not exactly pretty. You can see that's some grotty connections. That's why I was jumping about. There's something not. These breadboard connections aren't quite perfect. You see, the others are staying in place, so it's not exactly pretty, but at least it is giving an output signal now. And if just to show, if I remove that diode, gone, because the transistor saturates. So that by adding the diode converts that transistor to a Schottky transistor, and that was one of the big, almost revolutionary changes in early logic ICs in the 74 series, when 74 LS, which is low power Schottky, that's the LS stands for, when that was introduced, as all the internal resistor values could be much higher and the operating current much lower, because it didn't need high current loads to help the transistors turn off so quickly. It's just a very simple way of vastly speeding up a transistor. It also works for things like opto-isolator transistors. If you're ever trying to put a fast signal or even a moderate speed signal through an opto-isolator, such as working with MIDI data, or serial data, adding a Schottky diode between the base and collector of the transistor in the isolator will vastly speed up its response. Anyway, so that, if we get back on topic, that, let me just redraw this so you can see what I've done. That now has 2 diodes in the base. And the pull down resistor to stop it floating when there's no current through the diode. So that is now the circuit I'm using. Oh, sorry, there's a Schottky diode as well, a Schottky clamp, which is there. That's the total circuit I'm using. It's 2 diodes, so the input can be, or doesn't have to be, at 0 volts to kill the base current through those 2 diodes. Now that now needs about 1.8 volts, 3 diode drops minimum on that junction point there, before the transistor will turn on. So it can stand a significant offset at the input rather than having to be at exact 0 volts. And the transistor, as long as it's a sensible low level, the transistor will still turn off. Then that's the Schottky clamp that turns it into a Schottky clamp transistor or a Schottky transistor, which means it's a bit like negative feedback on an op amp in a way. When the transistor tries to turn on hard, when the collector gets down to about 0.2 volts, the diode's conducting, and it bypasses the base current from the pull-up resistor and stops the transistor turning on any harder. So the transistor is always in its linear region rather than saturated, and that makes it vastly faster switching, especially switching off. And this circuit, in essence, is the type of thing, the 2 diodes and the extra resistors, not with the Schottky clamp, because that wasn't invented back then, but the 2 diodes X resistors, and in that case, multiple voltage levels and different biasing to try and limit the saturation. This is what was used in early transistor-based computers before integrated circuits came about. So yeah, it was the 1960s era, or early 1960s, late 1950s. Transistor-based computers would use this type of circuit by the thousands for all the logic functions to build a complete computer. So it's there's not much they're used for now, but there are still people who build computers without ICs just as a hobby. There's quite a few online projects for those. I mean, it's not something, personally, it's not my thing. I've got way too many other things to do. Though I did try, before microprocessors became available, I did try building computers with discrete components and various logic ICs I could scrounge and find surplus online. But partly because a lot of the stuff was, back then all I could afford was these bargain bags of things which were a bit dodgy, manufacturer's rejects or whatever. I never got very far with that until microprocessor came out, and then everything worked basically. Though one of few other stories anyway. But I hope that's been of some interest and helps explain why some of the stuff you see online just doesn't work right. Which is a sad state of the internet. There's vast amounts of information, but a lot of it is not all that accurate, unfortunately. Anyway, thanks for watching. Please hit the like button and subscribe if you like this type of content. Okay, thanks and goodbye.